Got to have a great conversation with Joshua Schultz at the Steel Conference a few months ago. Every time we talk, I'm amazed at the depth of engineering he's familiar with, wild structures, a thorough architectural knowledge, and lines such as,
"Your analysis is essential but otherwise unimportant."
But since the conference is both for fun and education, the conversation can certainly lead to...
I only designed for orca loading.
So grab a seat and let's keep learning about lightweight structures. And if you haven't checked it out since the last discussion with Joshua, his book is such a fun read. We'll put a link in the show notes. It's a perfect story and resource. Really, take a look.
The Structural Engineering Podcast.
Well, thanks for having me back, guys. It was good to talk the first time, and so it's nice to be invited back. That's also kind of a confidence builder, right? Like, you get invited back to something, you're like, I did all right. I totally whiff it, right? And so, so I'm Joshua Schultz. I'm a professor at Gonzaga University in structural engineering and civil engineering. My background's architecture, so I've been in lightweight architecture and engineering for about 15 years now. And that spans a whole bunch of topics, some of which we've talked about. So whether it's cable nets or space frames or grid shells or structural glass, kind of all these niche, I like niche, kind of niche and beautiful. Yeah. That's what I enjoy working with. And so we're here at the Steel Conference and able to talk about, I think, a couple more topics from the book.
Yeah, we're excited. Yeah, and thank you for joining us again. I mean, our listeners,
that means we weren't bad, and so you're like, you'll tolerate talking to us one more time.
That's right.
Yeah.
And for the record, in person, which is really
way
cool. Nicer. Yeah,
way better than a computer screen. Well, something I wanted to ask is on our previous episode 103 about space frames, cable nets, and ETFE. I wanted to see, was there anything that we missed? Is there anything that after that episode you're like, man, I wish I talked about this, that we could talk about today before we jump into our topics?
Yeah, that's a dangerous, it's like a professional hazard to ask a professor if there's more they want to talk about. Right? There's more.
We're moving on.
Do you have 2 hours?
They're kicking us out of this room in 8 hours.
That's right. But I think it's good. I think the takeaway with those topics is you can spend an entire lifetime or a career on these. And so the point of probably what we're talking about here today and the book and all that is none of this is ever exhaustive. It's really just meant to be kind of a gateway to, all right, if you're interested in these kinds of things. And I think to be aware that these things exist. So as structural engineers, and maybe if you're more interested in kind of the architecture, like that, blurring that line as much as possible between architecture and structures. So not off the top of my head, but I'm sure we'll start.
Oh, yeah.
Today we're going to talk about grid shells. Well, that's where we're starting. And how do I picture it? Let's lay out what a grid shell is, just for people that are listening. Like, what are we picturing for a grid shell? What is the structural background of this? Start us off.
Yeah. So the beginnings of a grid shell really start. Well, again, we're engineers, so it's kind of on the nose, right? So it's a shell shape, and it's comprised of a grid or a lattice kind of structure. And so the way they evolved was from primarily concrete shells. So I think we were talking a little bit about this before we got on the show here. The idea of there's these sort of antecedent technologies, whether it's Candela or Eisler or some of these engineer architects who created long spans. And what they did was they used the geometry of the roof. So now once you have a curve, like an eggshell or anything that's curved, once you have that curvature, that's what gives you your stiffness. And so you get very, very thin structures, which is possible because of the curvature. And so that's really useful for concrete. That's also useful for membranes, like we talked about last time. But if you want to take and discretize that, and so what you can do is, if people are Googling, increasingly, what you can do is you could Google grid shells. And the idea here is if you think back to mechanics and materials, and you think about principal stresses and beams, and so there's those like lines where anywhere along the beam on these principal stress lines, you only have tension or compression. And so if you think about a shell, which is a continuum, and if we start to trace out the lines of principal stresses, and if we put the beams where there would have been principal stresses, now we can have the structure just along there. And what's useful for that is at least twofold. One is that we can use less structure because now we have a gridded structure instead of a continuum. And also, we can have that structure be as close to just tension and compression as possible. And then also it opens it up. So grid shells are often paired with the other thing we'll talk about today, which is glass, right? So you get these nice transparent kind of domes that can span, 150 feet or whatever you're looking at there is 150 feet is kind of that like perfect spot for grid shells. You can go beyond it, but 150 feet and below is really quite economical.
Comparing space frames and grid shells, is there a line that's like, if it's a thin enough space frame, it becomes a grid shell? Like, how do those overlap? Or is a space frame maybe can take some bending sort of if it's just axial, it is grid shell kind of? I don't know. How do I compare these things or think about these things?
Totally, yeah. So if we think back to a space frame is a terrible name, right? So it's you could go listen to, what is it, episode 103 or whatever. But it's a spatial framework is where the name comes from. But it actually is a truss, ideally. So it's a three-dimensional truss, and those only handle tension compression.
Okay.
And so space frames, usually you need a fair amount of depth because we need to be able to resolve those forces using statics. And so you've got tension compression and you've got, basically struts and nodes. And those approximate plate behavior because you've got the top and bottom chords that are effectively, taking the tension compression, and then the diagonals, just like a typical truss, can be approximated as shear. So space frames are effectively always tension compression. Grid shells, we increasingly are able to blur the line between perfect tension and compression. And so grid shells, the independent structure of a grid shell, so the actual members are going to be much, much smaller. So your structural depth there might be, 6 inches of steel depth, whereas in a space frame, you're going to have, 24 inches of depth or more because you need the space. So a grid shell, while ideally it's taking tension and compression, those members increasingly, because of stability issues, which we can talk about, you design those nodes to be able to have some flexibility. So space frames are very, very rigid. It has a lot of geometry on its side. Grid shell, the geometry is primarily that overall curvature. And so because you don't have a redundancy of members going into a node, you often have some flexural capacity so that you effectively don't get like snap through failures of your dome, especially shallow domes. It's a real danger.
Yes, and in the book too, there's a lot of examples of failures because if you get loading that is not uniform, which you always have, like things can snap through. Probably not giving a great example, and we'll talk about it later. But they can fail. So for visualizing here, I've been looking at a lot of like biophilia stuff, and we've talked about like we both have architecture-ish backgrounds. Like, is there a natural item that you would describe as a grid shell? And I'll give you the thing that I looked at, like is a seashell. Basically, is kind of that idea, although that is completely uniform. Is there some natural thing someone can picture as this is basically a grid shell?
I feel like I'm about to let my colleague and mentor Mark Sarkeesian down. He has all these antecedents from nature in his book, Tall Buildings, and so I think that grid shells are interesting. I haven't dealt with this question before.
The bending transfer, I imagine, is harder.
I think there's some inspiration from shells, obviously. So like actual continuum shells. But when I'm thinking of like lattices, the first thing that comes to my mind, it would be like your bone structure. So that's like kind of a lattice structure. Or like birds, their bones are much more airy, right? Much more.
That was actually a Google example that I was looking about this earlier. So.
Sweet. Okay. But I think in terms of like nature, where you'd see this, kind of what we were talking about before is the idea of principal stresses. And so if you're doing your topology, and there's a lot of sophisticated topology sort of out there now for grid shells, which lets you do freeform curvature by following the principal stresses. And so I think there, if you start to look back at like, Fibonacci sequence and things like that, so those sorts of repeated tessellations can give you sort of the raindrop-shaped arcs that those principal stresses want to follow. So I think that's probably where some of that inspiration comes from.
Okay. What about a building? Someone can picture a building that Well, we get into this discussion like what is something many people have seen, can think of that talks about space frames, that represents space frames well.
Space frames or grid shells?
Oh, sorry, grid shells.
Yeah, no. So in terms of grid shells, those are typically going to be, again, kind of roof-like structures. The ones that come to my mind are projects I've worked on.
Yeah.
Like the Transbay Center is, if people are Googling, they can go take a look at the Transbay grid shells there.
Okay.
I think there's, in the Middle East, there's some really interesting ones. You have Yasmal, and there's several other large articulated grid shells in that sort of building development that they'll go from like positive to negative curvature, and increasingly people are using the grid shell to come down and form like columns. So you can imagine like
Oh yeah.
this architecture, you have a curving roof, and then it's almost like if you poke through a piece of paper, that grid shell comes down and then connects to the ground. So there's grid shells. I think the technology and the architectural expression has come a really long way. And so there's at least a couple books maybe at the end I can recommend if people want to.
Yeah, that'd be great. Yeah.
What's typically the materials being used? Concrete, timber?
So not so much concrete. Concrete lives primarily in the continuum world. I would say that steel is, I think every grid shell, every grid shell I've designed is in steel.
Okay.
There are a number of really interesting grid shells out there. Oh, see, this helps trigger some of the examples. So there's a number of really interesting grid shells out there that have been done out of timber. So there's I'm going to mess up the pronunciation of it probably, but like they're the like Tijuana domes. If you Google world's largest timber grid shell, so there are these timber grid shells in China that were done by I think it was Structure Craft.
Yeah.
And they're just insanely cool.
They're so cool.
So I think timber and steel are kind of the go-tos. And what's interesting, I think, is that the detailing. So when you think about a grid shell, you have typically prismatic members. So we're approximating a curve with straight components. So you have prismatic members that are coming into a node. And so the detailing of those nodes lends itself to steel and timber. And you don't have to do too much changing. A lot of the detailing for the nodes for timber, you have like the lattice, you can imagine like 2x4 kind of thing where they're lapping, and you can bolt through them or you can strap them. And of course, it's nice and flexible, so you can actually get some actual curvature of the members. But it's similar to in steel, you have nodes and then you have the members coming in. So those sort of discrete elements in steel and timber play really nicely.
Yeah.
And they're kind of analogous in a way that, like, there are concrete grid shells out there, but I would think it would make more sense typically to just do a shell out of concrete than a grid shell.
Yeah, and thinking from like a construction standpoint, putting that together out of concrete or maybe precast could make sense, but timber and steel definitely make a lot of sense.
Yeah.
So from a design standpoint, how do you approach it? What are the challenges there?
I think that a common theme for all lightweight architecture is the idea of integrated design, or total design is what Ove Arup called it, or I think total architecture in my wrinkles with. Anyway, everyone always talks about the idea of collaborating early. Like everyone's pro it, at least verbally.
Yes.
And then like when it comes time to develop the team, it can be trickier. But so I think that bringing the team together early, and so what that might look like in terms of like nitty gritty details would be oftentimes you have a client who wants some sort of architecturally expressive element, and they'll work with an architect. And where it really starts with half the time I spend on these projects is being the lightweight consultant to the architect. So a lot of times the lightweight structures are a delegated design process. And so the architect, though, is going to need a lightweight or facade consultant early on to help them articulate in more technical terms what the design looks like. So this is like, we're talking schematic design, conceptual design, and also feedback to write, the specifications that are eventually going to drive. So that'll go to the GC. And so at the same time, the architect will engage an EOR probably for the main buildings. Sort of many of our listeners are probably EORs of the main building. And so the delegated design of lightweight architecture is going to go through, you'll have a facade contractor or consultant that works with the architect. They'll develop the specs and the preliminary design. That then gets parsed out to the GC. They'll send that out to bid usually. And that's where you're going to engage with specialty contractors. So those specialty contractors, there's a couple of versions of those. There's one breed which have the design in-house, right? So they can do the design and the install and oftentimes the fabrication. So kind of all there. Or, more common is that the subcontractor who specializes in the install of this will then go contract out the actual lightweight design through them, to make sure it's constructible and all that kind of stuff. So when we're talking about grid shells, there's 6 essentials, and I go through these in the book. And the first one is what your layout looks like. And so if you want a good primer in how to do this, Hans Schober has just like an insanely good, it's the book on shell design. And so the idea there is basically, again, there's very sophisticated with software and AI and all these kinds of different, finite element methodologies to lay out your topology. But the traditional way is basically you set up 2 curves. And so you can think of, an arch and another arch. And what you do is you take those 2 arches and you put them perpendicular to each other.
Okay.
And what you do is you follow the path of one of the arches with the other arch. And that develops a surface that's a curve. It's a semicircular surface. And so what it does is as you march this arch kind of along this pathway, along the translational arch, what it does is it gives you these lines and it gives you that sort of net shape. And that does 2 things for you. One, it develops your curvature, which gives you your structural depth. And so it's just like, if you're an engineer listening to this, you know that if I want a stiffer wide flange beam and maximize,
Deeper is helpful.
Deeper is better. And then the architect's like, you have 8 inches. And you're like, great, thanks. I guess it's going to be a 200-pound beam now.
Yeah.
But so deeper curvature is always stiffer. But that comes at the cost of later on when we talk about what we're going to clad this with for the glazing. As I get deeper and deeper curvature, it's harder and harder to have square pieces of glass that are also planar.
Yeah.
So step 1 is what that topology looks like. And so you lay that out. And from there, then typically you triangulate these. And so there's going to be typically offset just below the, rectangular HSS, which forms your grid. You're going to have these cables that are running to give you the triangulation for your stability kind of globally. And then once you've got that, there's going to be considerations about your connections. And so again, getting back to this integrated design, it's a lot of chicken and egg because every decision you make influences things that you don't.
Step.
Yeah, it's like the known knowns and the unknown knowns and all this kind of stuff. Where your different connections, you can make choices for complexity and for are they going to be able to, how much flexure and moment can they handle? And typically most grid shells handle some because you need that for avoiding both your local buckling and then your global buckling. So those are kind of the other 2.
If you have cables for bracing, sort of lateral or any movement here, are those at each node there? What's the word? Like if you had a cable, it would be locked at each node so that every little X is stiff in both directions.
I did an awful job putting words to this question, but Joshua's answer, it makes a lot of sense. So just skip what I'm mumbling about here and
Yeah. So if yeah, exactly. So if you imagine like just in plain, if you think of your typical engineering paper that's gridded, those cables are effectively going to connect on the diagonal in both directions. And every time that there's, a point on your engineering grid paper, that's going to be a node, and offset from that, there's going to be a fixture that the cables are tying to because the cables want to curve.
Yeah.
Right.
And so, but we don't want that. So we want to run those through fixtures at each point where the main members are going to intersect.
Okay. How much can you do? I mean, you were talking about the form here, but how much of this can be led by an architect's side, or is it to get an efficient design, they have to be talking to the engineer very early And, we're like, how much wiggle room is there if they say, we really want this shape? Say, okay, we can make this happen. This isn't the most efficient way to do it, but we can make this form.
Yeah, I think one of the reasons that grid shells are so attractive to designers is because you can achieve a lot of variety. So,
Okay.
of course, in an engineering realm, there's going to be these parameters that let you get to an optimum or perfect structure or whatever. But living in sort of the real world with all the additional constraints that make buildings interesting, you almost never have that. So, in the book, actually, we talk about there's two of these grid shells that are different examples. One is the Wrigley Innovation Headquarter. And so that's a good example where basically my colleague and co-author Chris Stutzky, he came to this project, and originally project was conceived as a series of trusses. So basically there was an existing building and they had a courtyard, and you're in Chicago. And so it cools off in the winter. And they wanted to be able to cover the courtyard because they wanted to keep they had spearmint and wintergreen and all that, because Wrigley makes gum.
Yeah.
And so it was part of their headquarters. And so they liked the idea of this area to be enclosed. And so the original idea was to just run a flat network of trusses, two-way truss system.
Okay.
Which technically works. But you ended up with really deep a lot of structure.
Right.
It was a lot of structure. So at the time, Chris talked to the architect, and the architect who has since passed away, but was Todd Halamka. He was familiar with the shells of Jörg Schleich. And so as a result of this, basically Chris was able to propose hey, what if we did this with a different structural system? And so by working with the architect, they went back and forth and they iterated, what was ideal for the look and all this kind of stuff. And the neat part about this project in particular is that as a result of iterating through with the architect, the structure ends up being this very minimalistic 150-foot span. It was one of the largest grid shells in North America at the time of construction.
Wow. Yeah.
And what's really cool, so in the book, I've got the different iterations of the structure hand sketch. And as they were studying the different iterations, what we saw was actually the more we leaned into the grid shell and got away from, so there was the truss solution. Then there's what if we just run a main truss down the
slowly
center
getting
of the
away from the
spine,
truss, yeah.
and all this kind of stuff. Well, and the further and further we got away from that, and the more we let the grid shell be the grid shell, the cost just kept coming down until finally at the end, the cost per square foot of the grid shell at the Wrigley Innovation Headquarters, on a square foot basis, it was the same cost as a typical skylight.
Oh my God.
Right? So you dropped hundreds of dollars per square foot.
Yeah.
Because you lost all that steel weight. So that's an example where working with the architect early on and shaping, the design and things like that can have a huge impact on efficiency and cost and things like that. Now, as another example,
going the other
to
way,
what you actually asked, is so then the other example we have is the Yas Mall, and so the Yas Mall is in the Middle East. And that grid shell had already effectively been designed. And so it had been designed with the lattice, the structure wanting to be patterned. So kind of like an Islamic patterning for geometry. And so largely it had been set, it was square. It was relatively shallow, but the general architectural intent was set. So within that, then you're not necessarily doing topology optimization, or you're not looking for that maximal efficiency. What you're doing there is you're saying, all right, within this preset structure, the design was, the design challenge was how can we optimize that?
Mm-hmm.
And then also it was working with the local manufacturers to make sure that they could design, fabricate, and deliver this. And so the key there was trying to come up with nodes that were reproducible throughout. So even though we couldn't necessarily optimize steel weight or overall layout, how do we optimize for cost? And that's going to be on the fabrication and install side, which is an important constraint because if that's not paid attention to, you risk failure.
Yeah.
So yeah, as consultants and lightweight designers, you can have participation early on, which is perfect and ideal in a lovely world that you get to do every once in a while. And then there's like, oh, here's this thing, make it work. And that's where I think, having partners in architects who really want to collaborate, even if things are locked in, and you have that dialogue of like, well, what are the things that are essential? And I think this is for every project, right?
Mm-hmm.
Yes.
What are those things that are absolutely essential that we can't change? And what are those things that we have the freedom to improve the structural performance in? You know? So those two examples kind of, I think, envelope, best to worst case or
I
whatever.
just really like these concepts promote communication with the architect, like we so often in the industry, just given what the architect wants and we make it work, but like there's no communication and we have to bid out every version and every option.
I think that, and then the connection with the contractor. If we could do that in the early, stages too, and communicate how they want to build it, man, that's a huge deal. So what about redundancy? How does that work with these structures and the idea of global stability?
Yeah. So it's really taken as an entire layout.
Okay.
So if you envision a grid shell, and so, going back to like, so the listeners, if they're trying to envision something, if you think to the like, when you buy oranges, right, that netting. So imagine that netting, and then imagine that you hang that netting, and then you freeze it in that shape, and you flip it over, right?
I like
There's
this.
there's your grid shell.
I like that a lot.
Or like a sieve, in the kitchen, or a colander or whatever. So, okay, mentally, that's your grid shell. And so when we look at this and we look at that process, working through kind of what that's going to look like. Sorry, I lost my train of thought here. So your
global stability, redundancy.
Yeah. So when we look at that as an entire system, that redundancy is really something that we have to check through in the design for the whole system. And it's tragic that I forgot your question, because it's like one of the most important things for grid shells. Oops. And so that stability comes in two things. The first is the overall stability of the global system. And that's like when I was a kid, there were these little like poppers. I don't know if you ever had these. And so they were these like it was half of a circle, and it was made out of this like little rubber plastic.
Oh, and it popped up after
and
a while.
And you flip it through, and it would pop up in the air after a while. And so that's like, quintessential snap through kind of behavior, right? Or those old snap bracelet kind of things. And I'm really dating myself. So like all the Gen Z we just lost. But anyway, so global stability is really huge. And that's kind of your traditional snap through buckling behavior. And the way we look at that is looking at the overall stiffness of the entire structure. So you load that up, and like you were saying earlier, is you've got a uniform load, but you also will oftentimes have non-symmetric or asymmetric loading. And so you apply that, and typically for this and for the next check we'll talk about, you want to do that incrementally. So like if you just take a shell and you perfectly load it up, shells are very, very strong, right? Like if you ever take an egg and try to like squeeze it to crack it, it's very difficult to do. So the idea of like a uniformly applied load to a grid shell, it's going to perform wonderfully, perfectly. So what you want to do is you want to analyze that incrementally by increasing that load, and also introducing the tolerances that you're actually going to have in construction. So in the book, we talk about, there's many examples of this where you'll have grid shells that were designed totally fine, but your tolerances for grid shells have to be handled differently than standard steel. So standard steel, we're used to like, maybe a 16th, and, you get your columns and you can install it and all this kind of stuff. And that builds up, and it's fine though, because primarily our columns and beams are bending.
Right.
If you have a structure that is basically, a three-dimensional arch, and each time you have a connection, you're picking up a 16th of an inch of flexure over 20 of those connections, all of a sudden you have multiple inches.
Yeah.
And so now you've got slack in the system. And so there's examples of where, in Munich, in the book we talk about this, in Munich, there was a shell. It was designed by a very well-known, very good engineer. It was designed perfectly, but in the bidding process, the contractor was someone who didn't have experience with shell design. And so this, again, is a point in all lightweight structures. You really, someone, ideally multiple someones, but someone on the team needs to have prior experience with whatever it is you're doing. And so the contractor was unfamiliar with kind of the construction sequencing and processing. And so as you assemble this, what ends up happening is basically you pick up these tolerances.
Yeah.
And so the tolerances, they built the whole thing, they glazed it, they put on all the glazing, they went home, they came back the next day, and the shell collapsed.
Oh no.
Yeah. I'm sure they said some version of oh no. And so there was a whole study, and no one could find anything that was wrong. So insurance actually paid it out, and they rebuilt the shell, and they reglazed it. And then I think on the second go around, I think it snowed, and the next morning it collapsed again. And so there was a whole forensic investigation. What ended up happening was, again, going back to these tolerances, the tolerances had not been properly accounted for. And so it made your shell much less stiff than was accounted for. And so that's one of the concerns of the design. So getting back to your question about like robustness and multiple load paths, the grid shell, if it's designed against global and local buckling, there's kind of a multiplicity of load paths, but it all has to work together, because if you lose one of it, the whole thing's going to give in. So then the second consideration is local buckling. And so again, there's another example in the book of this failure where you had a grid shell. It was a giant aluminum dome over a storage tank, and it was designed fine. It was erected, and it did not collapse the next day, which is good. But later on, there was snow, and the snow was applied, and the snow was applied non-uniformly. So what happened was there was not a global buckling issue, but as the snow aggregated on one side of the dome, what that does is it loads certain members more than other members. And so those members and where they connected to the nodes started to yield.
Ooh.
And so as those start to yield, they shed load. So what ends up happening was it's not necessarily the yielding of, member A, but as member A starts to give up its load to member B, now that member is going to get more load, and so you're going to encounter local buckling. And so what happens is if you don't slowly increment your load in your analysis, you'll miss that, because if you just check global buckling, if you just do a buckling analysis, it's fine.
Yeah.
What you have to do is you have to go through and you have to step through the load scenario, and you have to make sure you're not yielding obviously any of the nodes, and also getting to any sort of local buckling. So to answer the question, there is not necessarily like a redundancy of individual parts, but if the whole thing is designed as a whole, then you're going to be okay. So yeah,
you, Max, may have talked about this before in the other episode, but from a review standpoint, do you peer review these projects, or I'm just thinking most contractors
really critical. Like these are so sensitive to a mistake, and someone that hasn't done this, like nothing but what you were just talking about. If it's the first one you've done, it's probably a bad idea to start. But like, not think about everything that is involved in the design.
100%. Well, and that's the chicken and egg, right? Is, well, how do I ever do these if I've never done one, right? And so again, getting back to integrated design process, whatever, like 40% of my design work has been as the consultant to the architect working on schematic and conceptual design up front. And then maybe 40% has been working as the consultant or the engineer for the contractor. So that leaves like, what is it, 20? And all, like 50% of all statistics are made up or whatever it is. But anyway, one of whatever that remainder is, I've done a fair amount where you'll have engineers who are engaging in lightweight structures maybe for the first time, or they just want a second set of eyes. Or if you're doing something new and novel, I think it's really useful to just have a sanity check, and it's well worth it. So frequently I'll serve as a peer reviewer for engineers who are designing grids or cable nets or things like that, because there's so much that you just learn over time by experience.
Yeah.
And that really increasingly has such value, because you can say, oh, like, here's this apparently small detail and you don't want to do that. We want to do this, or, because you're juggling a lot of things. You're juggling complex geometries, kind of weird load paths, not necessarily, I wouldn't say there's necessarily like less redundancy than a typical building, because if you lose a column in a building, you're going to notice it, right?
Problem, yes.
And so unless you're doing like the FEMA analysis where you actually planned for it,
Aggressive collapse. Yeah.
a column going, you're going to notice. So similar, right, in a grid shell or space frame or things like that. But there's these nuances of, you can have stresses develop, or you can have, the construction sequencing is so huge that if you don't have that experience, it can be really valuable to inform your design. So I think one of the ways that you can benefit from this is tracking down and finding people who've done it before and are, more than happy to kind of share that experience.
Yeah. I like that you just mentioned construction sequencing, because that's what I was thinking about, is like, does that influence the design, making sure you can construct this in a reasonable fashion? Like, are those thoughts into what is put out there eventually?
Yeah, 100%. And a lot of this goes to those contractors who, they're specialty contractors. They know how to, erect the steel and do this sequencing. I think we talk about this a little bit for the Trans Bay project. So that was a project that benefited. So it was a public project, and it benefited from like years of, schematic. There was like the schematic design phase. There's the bidding phase. There's all this. But even once you get to the site, I always say, in theory and practice are the same, and in practice they're not. And so as soon as you get, I think Mike Tyson says it better, right? He's like, everyone's got a plan until you get punched in the face.
Yeah.
So, if you've ever been to the job site, it's like, well, I had this plan, and the bolts are, the bolt holes are over here. Okay. So I think, that really is, it's hard to describe. If I had to pick only one person, only one additional team member who had experience, I think the contractor, they're just gold, right? So like the ability to troubleshoot with someone who's, erected these and coming up with solutions with them. So I think, ideally, you probably want at least two people on the team who've done it before. Someone on the design side, and then someone there on the construction side. So the sequencing is remarkably challenging, but a lot of that rides kind of on the shoulders of those contractors and the erectors.
What does that shoring look like? Like, what is that? Can you walk us through the shoring or sequencing of that? Is it worked once the last piece is put in, and now we can pull everything out? And
yeah, the nice part about grid shells is, other than the self-weight of the steel, there's not a whole lot going on until you clad it with the glass. Right? And that's where, the next morning, hopefully it doesn't collapse kind of thing. So a lot of times, most grid shells aren't designed for pure axial loads. Most grid shells, and even if they weren't designed for it, most of those nodes have some ancillary capacity where they're going to be able to transmit those. So that, coupled with, a minimal amount of shoring, is going to get you. So the actual maybe like erection process might not be that difficult, might not be that different from like a sophisticated steel erection where you have a lot of straight beams that are like on an incline and things like that. So the process is going to be very similar there. And then what's going to happen, so in terms of sequencing though, is so you'll go through and you'll erect that steel, kind of building from, typically you'll have whatever your edge condition is, and you'll erect upwards in multiple places. And then it's always like, it's kind of like the St. Louis Arch moment where you're like, I hope this comes together. But again, there's enough place so that you can usually pay attention to that, or you're aware of it increasingly now on the site with all the level of detail we have with, laser leveling and all this, like, and again, that the contractors who do this are worth their weight in gold. So, and you can make those adjustments as you go. And that's detailed in as well. Like you can pay attention to that. So you build that up. Then what you're going to do is, you'll have probably run the cables through to what we were talking about earlier. And then, the steel as erected is going to have a fair amount of stiffness.
Yeah.
And then once you lock in those cables, then you're good to go, right? And so then typically what you do is after that, you come through and then you'll start your glazing. Sometimes they'll phase that, but ideally you're not glazing until all the steel is up because you don't have any real stiffness.
Yeah.
So typically it's steel, cables, glazing.
That makes sense. Are these structures mostly saved for iconic architecture? Like from a cost perspective, you brought up one project where it became, better to have a grid shell for the roof, but you find that you think more projects could have grid shells, and it's just that maybe the design world isn't aware of them enough or has the knowledge base.
I think that's fair. I think grid shells can be cost competitive, and especially for the aesthetic that you get.
Yeah.
Space frames, because of their very nature, lend themselves to cost efficiencies because they were literally designed for mass production.
Yes.
Right.
Grid shells, you're not going to have sort of these like as many of these proprietary systems out there where you can just kind of pull one off the shelf and apply it. But when done, like we talked about, you can save tremendous amounts of steel, and you can also have pretty rapid erection as well, sequencing. So I think, it's very possible that grid shells can be very cost competitive.
It's possible. We can do them.
Yeah.
Yeah. Yeah. It's a lot of it goes like, and this is the integrate. If you have a client who is willing to entertain it and, has seen the successes before, so you could show them the Wrigley one, like, look, this was a sky, take a skylight and multiply it, by 1,000. And that's your cost. So I do think that it can be cost effective in a way that like, cable nets there's a premium for a cable net over like a traditional mullion storefront or something like that.
Yeah. Makes sense.
Okay. I want to get into glass now, but is there anything in the cable net that you want to say and just like
grid shell?
Oh gosh. All right. Anyway, anything in the grid shell that
We can tell what your favorites are.
You need more coffee?
Yeah, I know. Anything that we
I
can
think
talk about?
because what we'll do, I think, is in the world of glass, so we'll probably pivot to structural glass.
Yeah.
Mm-hmm.
But the reason that glass is in the book actually is not because glass is lightweight, right? So glass weighs basically the same PCF as concrete or granite. So glass is very heavy, but it has this aesthetic of lightweight. And the other reason that it is because it pairs nicely with lightweight structures. So your grid shells, not so much your space frames, but your grid shells and your cable nets end up getting clad with glass. So either glass or membranes are kind of your two options. Yeah, I think we can go there. And that's the dangerous, like, I will geek out on glass forever. So
you've written a book on this, so to ask, like, do you have any other detail? Like, well, yes, a lot.
They'll just quietly turn off the mic.
He's going to open the book and just start reading from page 1.
All right, we're going to glass.
Yeah.
Let's do it.
What, kick us off there. Like, what are the types of glass that we use in the structural glass, especially? Like, is this the same glass that we have in our window? Give us the baseline for what we use in structural glass.
Yeah, so the term structural glass is kind of defined by the negative in the sense that architectural glass is defined and structural glass ends up being kind of not that. So architectural glass is the glass that is typically associated with windows. So it's historically four-side line supported glazing. That's in a mullion or in a window frame. And so in the US, ASTM E1300 is the go-to for glass. And that started for architectural, air quotes, glass and is now really the place you go if you're doing structural glass as well. Because we don't really have any codified standards. I think there's a couple through like, the NCSEA and things like that. They have a couple guides.
I'd imagine Europe's probably way ahead.
Eurocode is,
Yeah.
Eurocode has codified glass. And then actually there's also if you're looking at glass fin design, which we'll talk about, I'm sure, the Australian code is historically was where you found glass fins. So structural glass is the glass that is actually carrying load beyond just like a wind load to a mullion. So when you talk about structural glass, that's going to be everything from glass stairs and walkways to glass balustrades to these giant glass walls that often have glass running perpendicular that's taking the out of plane, and those will be glass fins. So the glass as a material doesn't fundamentally change between architectural and structural applications. We have 3 types of glass. We have annealed, heat strengthened, and fully tempered glass. Annealed is not typically used for almost anything anymore. That's like, that's the like when you drop a glass in your home and you get these giant like weapon like shards, right? We don't use that in our buildings.
I don't understand that. Yeah, why not?
So we are always using either heat strengthened or quite frankly, fully tempered. And so in the tempering process, you take the glass. It's been, so the way that glass is manufactured is it's called float glass because you melt all the materials down in a furnace for glass. And actually what you do is you have the molten glass and it comes out and it floats on a molten pool of tin because tin's boiling point lets you have the glass that can kind of start to cool on this molten. So the reason you call it float glass is because it floats out
molten. Oh my gosh.
Yeah. And so
like Star Wars.
Okay. And so as you have that, so you have this glass, and then if any of the listeners wear quote unquote glasses, even though they're polycarbonate lenses, probably you'll see that like there's always these little scratches that develop, right? And so glass has all these microscopic surface flaws. And so what happens is perfect glass, which doesn't exist, is very, very strong in tension and compression. But you can't make perfect glass. It always has these like little surface flaws in there. And so these little tiny microscopic cracks, what happens is those act as little stress risers. And so whenever you apply a load there, that starts to propagate the crack through the glass. So glass actually doesn't necessarily fail at the highest stress point. It fails at the highest stress plus flaw. So if you imagine a stress distribution, think of a plate and you've got your, kind of rainbow stress distribution here. And then you overlay on that a random sprinkling of flaws. It's the worst combo of flaw plus stress, which is going to propagate failure.
Yeah.
So what we do is we take the annealed glass and then we temper it. And so when you temper it, you basically raise the temperature up and then you quench it really fast. And so what that does is you get pre-stressing on the outside. So it sucks in. And so what it does is you get compressive stresses at the surface, which close those flaws. So just like in pre-stressed concrete, where my concrete doesn't feel anything until I overcome the pre-stressing of the steel.
Right.
So too in glass, the flaws don't open up until I've overcome the compressive stresses at the surface. So that's fully tempered glass. And that gets used typically in both architectural and structural applications. So that actually is one of the technologies that you needed for all these modern glass applications is the idea of fully tempered glass. And increasingly, we have better technology and larger furnaces and all this kind of stuff. So the pieces of glass are getting bigger and bigger and bigger and clearer and clearer and clearer, and that tempering process as well. Because if you ever have a chance to go see how glass is manufactured, even if you see like
where can you go see this?
Yeah, that's a great question.
I would love
there's
to.
Not a lot of them, and so but maybe analogously, if you can get to a steel mill, right?
Okay.
So they're running this continuously, and you've got the glazing, and then you've got these giant pieces of glass, similar like you've got these giant steel members. Well, you're limited in your design. So this gets back to the holistic picture of design. Is like, what can I actually buy and what can actually be tempered or laminated?
Yeah.
And so your sizes are based not on the sheets of glass you can get, but rather the sheets of glass that can be tempered, because that's a different furnace, and then laminated. And so the laminating process is basically your car windshield, for example, is fully tempered glass that is laminated together with a very flexible PVB kind of joint. And so that PVB is a very flexible glue, and what we're going to end up doing is you glue those together, and that's what gives you sort of redundancy. You've got two pieces of glass that are glued together.
Okay.
Yep.
So to get more strength, you're just gluing more glass together?
Yeah,
Bringing more
it gives you
layers?
both more strength, and it gives you were asking before about redundancy.
Right.
Yep.
Okay. So what members are we using with glass? Bending member, beams, columns, I mean, a little bit of everything?
Yeah.
Roofs,
Yeah,
floors,
so-
walls?
A lot of plates, so you're going to get stair treads. So it's operating in bending.
Okay.
Glass is operating in bending, and so your design fundamentally is at that tension surface in your beam bending at that tension surface. That's what you design for.
Yeah.
So you increase basically the tool in your tool belt is thickness of glass and number of layers, and depending on to meet the stresses. So the floors, the balustrades, the walls are all bending, and you're designing for strength of glass, thickness of glass, and number of layers.
Huh. It's pretty cool. So what would you say are the biggest misconceptions that engineers have with glass? I have one in my mind, but I'm curious.
Yeah, I think, and so I've worked with glass, like my master's thesis was on glass. I've done glass kind of my whole life, so I've been inured to the emotional baggage that I think a lot of engineers, when you think of glass, you don't think of like, oh, there's a material that's very forgiving and looks very strong.
Yes.
Right.
And to be fair, if it's not properly engineered, it's not.
Yeah.
Yeah.
I thought the tension thing that you mentioned, that it's actually strong in tension if it's put together very well. Like was picturing it like concrete, where it can be put in compression, but tension is just not even close. But you're saying the material is okay in tension. It is the little flaws that make tension difficult, kind of.
Correct. Yeah, 100%. And actually, like that goes into this answer, I think, a little bit is, so I think that it's very fair that glass gets perceived to be either not as strong, and air quotes around strong, right? And also, when you think about glass, you think, oh, that's a brittle material that's going to fail suddenly, which is true if it's a single piece of glass that's not laminated together. So, the reason I think it's worth sitting with glass behavior and what that looks like is because glass behavior for fully tempered glass that's laminated together, those two technologies ameliorate the challenges of the brittleness and the sudden failure. So I assume that the primary baggage, when we talk about timber, for example, right away you're like, oh, it burns.
Yeah.
Like, oh, well, mass timber chars and all this other kind of stuff. That's a whole different podcast. And, glass, I think it's perceived to be quote unquote weak and then very brittle. And so as engineers,
what's the stress strain curve look like?
Well, so it's linear until it fits. Yeah. And so where you get some ductility post breakage is by laminating those sheets together.
Yeah.
And so oftentimes, if we follow, so basic mechanics is going to follow here. So if you think about your Bernoulli-Euler beam that you encountered in mechanics of materials, the stress is very linearly as we go from the neutral axis all the way to the extreme fiber, and we have maximum stresses at the surface. So the good news is that the maximum stresses are going to happen at the outermost light. And so if you have a bunch of layers of glass glued together, well, the outermost light will fail first, and that'll kind of crack. That's where you get the crackly pattern,
Yeah.
So it'll crackle, it'll fail. It will no longer give you strength, but what you're going to see is that you'll still have enough strength. Typically, the way you design this for strength in a floor or a stair is that bottom light is sacrificial for strength. So typically, that bottom light is giving you your stiffness requirement, your deflection requirements, but it's not critical for your strength. So if you go to the Grand Canyon, there's a glass bridge walkway you can do.
Been here, right? But been to this thing?
No.
Okay.
Oh, yeah.
I've been on the Sears Tower.
I was going to say, that was the next one, Sears Tower. And then the Hancock has not to be outdone, right? So the Sears Tower has the ledge. So, and so that was engineered. Obviously, Sears Tower was really SOM, and so the ledge was in part done by SOM as well. And I think Arik was on the the ledge engineering for that. And then, not to be outdone though, the Hancock Tower, which is also an SOM building, has the tilt. So they have this glass experience where you can it leans out. And then actually, if you really want, the glass experience, China has these insane glass bridges and even though intellectually, I've designed this for 15 years, you're always like, a little unsure. So all those applications have an extra sacrificial layer for strength. And so even if you see a glass light, that's going to have residual strength there. So that's how you hit that.
How is glass communicated? Like in the construction drawings, I think, how beams are called out are pretty straightforward, but how do you call out glass? Is it thickness? Is it?
Yeah. So in detail, right? So you'll call out sections and details, and in the details, you'll call out explicitly, and you can change the thickness for every light. Wow. Every layer is called a light. So you have the LITE. So each light of glass can have different thickness, and there's standards and all this kind of stuff. It's in ASTM E1300. So oftentimes what you'll do is you'll say, 5 layers. The outer 2 can oftentimes be thinner, so because they're sacrificial. So you'll have thinner layers. You call out the inner layer, which is typically a constant thickness, and so you call out 5 pieces of fully tempered 1/2 inch nominal glass with PVB, or typically for structural applications, you'll use a SGP. So there's a Century Glass Plus, and that's a much stiffer inner layer.
Okay.
And so it gives you real, a great degree of improvement on your deflections. And so you'll call it out in that level of detail, which again is where the challenging part is this, unless you happen to sit through one of my classes, glass isn't taught typically in engineering school at all. And so either you go to a firm that does this, or you kind of have to seek out these resources that kind of reach you.
Yeah.
Yeah.
I can't think of many of the softwares I use and design on a daily basis have glass built
button.
in.
Yeah.
They
there's very
it does.
They don't. So historically, it's probably still out there. I would always do my design historically in an Abacus or a high level FEM.
Yeah.
But if that's not a light. It's an expensive software, so it usually isn't worth it for a lot of people to buy for one glass project.
Yeah.
Historically, there was a European software, MEPLA. It's probably still out there. MEPLA software, which was for point-supported glass, which I guess we haven't talked about yet. But that's basically if you drill holes through the middle, and then you've got these point supports, and then it makes your glass design even more complicated because now you're aggregating all the load to you just cut a hole in the glass, so you have stress increases, and so. The devil's in the details, or God is in the details. Mies van der Rohe says. So with the different sort of applications, my favorite software, and I joke I should get NASCAR or something. Is a Delubel software, RFEM. They actually they have a glass module in there, and the Eurocode is very, very robust. The ASTM basically just does a maximum stress check, which is technically okay. So I would say that of what I know about on the market, the only one I know of is Delubel has the RFEM. They have a module in there.
Okay.
Cool.
Yeah.
Connections. You keep jumping. You're correct, or not jumping, but your expectation of what our next question is going to be is correct. Connections. How do these work in glass? I have no guesses. I'm picturing Mullion just slides in, and then there's nothing fixed or whatnot. How does this happen?
Yep. So the third of 3 structural innovations that give us modern glass structures is structural silicon. And so you had fully tempered glass, you had laminated, and now we have structural silicon. And there's different manufacturers out there, but it is exactly what it says. It's a silicon that's been designed to carry long-term shear and tension loads. And so that's important because when you have different pieces of glass, sometimes you'll have just standard caulking that's just for the building envelope, but every once in a while you'll need some sort of structural component to effectively glue these things together. So that's one thing. But increasingly this is done with, I think, very beautiful hardware. And so the 2 types of hardware that you have are either edge support clamping style hardware, or you have point supported.
Yeah.
And so the point supported is where you have holes in the glazing that is drilled through. And there's a whole sort of side tangent that we don't have to take, but basically like, how do you manufacture that? Well, you have to take your annealed glass, you have to drill it with either, you could either do like a diamond bit or water jet. Water jet is better because it's less damaging to the glass. And then you have to laminate that, and temper that further down the line. So anyway, if you have pieces of glass that have holes in them, you have two things that are challenging. One, you just drilled a hole in the glass, so you have stress concentrations like everyone learned in school. And also you have your maximum loads, because typically those supports are going to be, oftentimes there'll be a cantilever balustrade, or you'll have a giant piece of glass and it'll be supported at the corners. So you have a giant moment arm.
Yeah.
So the way that you connect these is either, again, like with the structural silicon in consistent sort of, edge connections, or you have edge clamping. And that simplifies your design considerably, because you quote unquote only have to worry about all the other things we've talked about to this point. The other type of hardware is point supported glass, or PSG. So oftentimes you'll have like a FT, so fully tempered PSG, point support. We love the acronyms, point supported glass application. And so those, again, there's some commodity out there. So there's different companies that make sort of commodity pieces. And then there's also some great companies out there that do really high level precision engineering work. Colleagues at Tri-Pyramid, they've done everything from like the Louvre to actually at the steel conference that we're at right now. They've developed like a ductile bracing that under seismic events doesn't yield for these connections. So they're so that'll be in public domain by the time this thing goes public. So those are kind of the two different breakdowns for connections. Is you have mechanical fixities, and then you have structural silicon. Of course, the structural fixity is going to be metal. So oftentimes it's stainless steel. And in between the stainless steel, you don't want to clamp glass with stainless steel. So in between that, you're going to have like a soft rubber, an EPDM rubber, which is just like a rubber washer, so that the glass doesn't come in contact with the steel, because that's what's going to shatter your glass. So you want to always basically like mentally have your detailing with like kid gloves, where you've got like the glass never touches anything that's steel. It's always going through a silicon caulking or some sort of like rubber seal.
So when I think through a lot of our structural connections, bolts, screws, welds, etc., those things aren't really maintained. But with this, you're including or adding pieces that seem to need maybe replacement with time. Is there maintenance to these systems? If you're adding rubber, or
the structural silicon falls into a similar category of traditional caulking and silicon there. And so the lifespans for those, I don't want to like misquote the manufacturers, but if you check there, I'm sure it's, it's like 25 years, 25, 30 years or something like that. Maybe more. So the structural silicon is typically not exposed to the weather. The washers and the sort of EPDM rubber, over time that could have some degradation from UV and things like that. I've now done this, long enough where there's a bunch of projects I'm familiar with that I've designed that have been around for like 15, 20 years. And we haven't had any failures or anything like that. But like everything, there's going to be some sort of maximum end of life. And what is often going to go will probably be like the structural silicon, or maybe those rubber pads might fail. A lot of times, increasingly though, structural glazing is also going to be subject to thermal considerations. So this is like the peak, and the last project we cover in the book is Grace Farms, which is just like this it's just super sick. It's so beautiful. It's this like long curved glass wall, undulating kind of thing. And that is structural glass, but it's also IGU, insulated glass units. And so oftentimes what your limiting factor is on lifespan is the seals on your IGUs. And so, because once those seals go, then all the thermal value of that system is no longer present. And so in that kind of realm, again, you're not at a 50-year span. You're going to have to replace that, which I'll say as a caveat. I don't know if I'm preempting you again or not. Is when you're considering the sustainability impacts of IGUs, you really have to be honest about what the lifespan is there. But anyway, so yeah, there's some consideration there, but typically it's pretty long. And I haven't actually, to my knowledge, had any structural glass failures that came from the rubber degrading yet.
Okay. I think the sustainability thing and longevity is such an interesting discussion point to have. I had a project a few years back where that was the big driver, and they said, okay, so how often do we replace the deep foundations? And I said, I don't know. You're asking. They said, well, we need to put it into our, this is a 300-year building. How we'll have to replace them at some point, right? And so I don't even know how to answer your question. What? So I find, it's total side tangent. The sustainability and longevity conversation in structural engineering is fascinating to me.
Yeah.
So
you did have one thing that was very similar to my next question to be. So, but it's a dark question. The failures of glass. Are there any conditions of a historic sort of failure where we got to learn a lot about glass? But I don't think I can't think of any, but
yeah, not at the level of Hyatt Walkway kind of level of things have failed. The tricky part is glass is so lightweight structures like cable nets and glass applications are expensive. And so
yes.
Oftentimes when there are failures, there is significant cost involved.
Yeah.
And so usually the failures that we're talking about fortuitously are not loss of life.
Yeah.
But they can often be quite expensive and potentially litigious.
Yeah.
So the good news there is it's not life, but it is dollars.
Yeah.
And so also as a result of that, because insurance and legal and all that kind of stuff, there's not probably as many of those publicly articulated for obvious reasons. But on the whole, there's not a lot of those failures because there's typically redundancy. Typically things aren't getting overloaded in that way. The most obvious ones would be stairs and walkways, and like we said, those get over designed to get another layer. Balustrades, where you might have someone leaning on them, they're designed for 200 pounds.
Yeah.
And then they have a handrail as well. So typically the nice part about glass is it lets you know something's wrong because it'll crack and there'll be a shattering, and then all glass everywhere as soon as that happens.
You'll stop leaning on it.
It needs to be replaced.
Yes.
So there's not any obvious one like that. Yeah.
do animals get on there and crack it? I'm thinking birds. Hop on there.
Oh yeah. Because we talked about. Yeah, I think we talked about in
yes,
ETF,
yes,
birds pecking. So there is a real realm with all these glass facades. You get bird strikes.
Yeah.
And it's not nothing. It's a real concern. So increasingly, this kind of goes more to the architecture side than the structural engineering side, but they're putting on, bird safe glass, which is increasingly, you have a printed pattern on the outside. So the birds can recognize it as not perfectly clear, or it's not the clarity, it's the reflectiveness, right? So the glass that's perfectly reflective, it doesn't register. And so that's where birds are flying in. But even that isn't, it's going to kill the bird. Unfortunately, it's not going to probably lead to glass failure. But that's largely on kind of the architectural side.
Yeah.
We had a little side conversation and distraction in our Steel Conference lecture room, so I'm jumping back without a good segment, but I want to make sure that this part of the conversation fits in there.
I'm curious, when you go to aquariums or things like that, is that structural glass? Is that a different material? How do you know what they're using?
And also, how thick is that ish? I just guess, is this 7 inches?
Right, we'll go to the aquarium tonight.
Yes,
for dinner, and I'm so curious.
And so what's interesting to me is I actually haven't done any aquarium designs.
Yeah.
And so it's a little outside my milieu, I guess. But it's often very, very thick. But what it benefits from is you have uniform loads, right? So it's a giant water tank.
Yeah.
So your loading is very consistent and you know exactly what it's going to be. And then you have full supports on all four sides or all three sides typically. So while the loads are very, very high, I think analysis is relatively straightforward.
Version.
Yeah.
Okay.
So it's easy to encapsulate the best or worst case loading scenario.
So I remember from episode 103 when you and Max were talking with cable nets, the tolerances to the structure was a big deal, and then the structure could take the load was huge, and the stiffness of that. When it comes to glass design, I'm guessing this is also a delegated item from tolerances and fit up to what the EOR is doing. How much challenge is there? Because there's no stretching the glass. Right?
No, 100%, yeah. And so there's kind of two groups we could put structural glass. We could put structural glass into sort of the more separated install type stuff. So like a stair, whether it's the treads of a stair or the balustrade of a stair or things like that, where the glass is a structural element and it's just part of the load path and it's being designed for kind of your standard L over 240, L over 360, applications. But then when glass is paired with cables for cable nets, that's probably the big one. So when glass is designed for cable nets, it is the weakest link in the sense that its deflections limit the design. And so you have two options. One is you thicken the glass so it can absorb these very large deflections that you're getting in the cable net wall. Now, the cable net wall, to go back a little bit, is as that cable's deflecting, even though you might have very large deflections in the middle of a wall, you have kind of time, you have space where like the glass panels bit by bit are deflecting. And so even though you might have a very large deflection in the middle of the wall, the whole panel's deflecting kind of consistently. The worst case scenario usually comes at a corner or at an opening where one corner's deflecting a whole bunch and the others are not.
Yeah.
And so your design is either make that glass light really, really thick to try not to have it fail, or typically what you do is you have like a sacrificial light, because you have to design the cable net wall to like, whatever, a 50-year event or a 100-year event. And so typically what you'll do is you'll say, well, when that 50-year or 100-year event happens, we're just going to anticipate that one piece of glass is going to break and we're going to replace it because it's far more cost efficient and more sustainable to have that one thing replaced than size up this whole system in an attempt to still not have it break. With grid shells then, the design there is a little bit more interesting, where you've got a rigid structure. So the deflections aren't necessarily the issue, except that when we were talking about grid shells, you've got this curved surface. And so when you try to take a curved surface and make it into a whole series of squares, you can do one or two things, but not both perfectly, which feels like the story of my life. Yeah. Like, you can do lots of things, but none of them perfectly. And so you can either have it stay relatively rectangular so that it's not warping in plane, so you get like diamond shapes, right? Or triangles. Or you can keep it flat, planar, but then you might have some warping because of the way if you take like that cable net system or the grid system or the colander in your kitchen, right? The sieve, like if you look at that wire, as it deforms, it's not a whole bunch of squares, right? They all want to move a little bit.
Yeah.
And so what you're left with then is if you can design the curvature gradual enough, you can sort of eat up or absorb the imperfections in the silicon caulking, right?
Okay.
If not, then you have to go to special glass shapes, or you have to have curved glass, which gets very, very expensive.
Yeah. From a manufacturing standpoint, they're not coming out and measuring how everything's actually in the field first and then doing the glass. The glass is getting made at the same time they're building this grid shell or the cable net?
Yeah, ideally to keep costs down. So if we want a cost-effective grid shell, we need to stick with planar glass. Like
Yeah.
curved glass is going to be more expensive.
Yeah.
Even if it's cold bent. So like you can actually
Cold
yeah,
bent.
yeah. I got this look of like a bit of bent.
I need
So
more.
there are tolerances. And so there's some good stuff out there. Keith Boswell and his group, there's a committee out there. They talk about cold bending of glass. And so increasingly, there's a good knowledge out there where you can take flat sheets of glass and there's a certain amount that you can bend it without it breaking.
Huh.
But so whether it's either designed and manufactured so it can be cold bent or it's, curved in the factory, that both of those are way more expensive than if I can have flat sheets of glass.
Yeah.
And so in terms of cost efficiency, we want to keep that as flat as possible. And so we want to be able to buy flat square pieces of glass. If I can't have that, then the next thing is to do planar non-square shapes of glass. And so that adds some costs. And then if I have to do some, either cold bending or bent glass. But typically we want to stick with planar pieces of glass wherever possible.
So the tolerance is more in the gaps.
Yeah, to your point, there is tolerances there. And so the tolerances for the glazing system, it has to be detailed out and accommodated for those gaps or the caulked sort of connections. And the key often there is like there's going to be a point where the two pieces of glass want to get maximally close together.
Yeah.
You have to make sure that they're not. That's like the limit case.
Yes.
And then not too wide so that all of a sudden I have a 3-inch caulk joint or something.
Just cover that with something. All right. Is there a project? This is both for like the visual of a perfect project, but then something that represents structural glass to the best version that you could think of. Like, is there a representative project that someone can look up online?
Yeah, I really am proud of, I think the Grace Farms project is a beautiful project, not from a pure structural sophistication. Although there was a lot there. There were very large pieces of glass that we had to make sure they had proper, EPDM sort of sealant at the bottom so that it didn't fail and all this kind of stuff. But because it was the project is really interesting because the nonprofit that it's for has a really interesting sort of mission, broader humanistic mission, which is really cool. And also the design was like peak integrated design. So you had architects, you had an engineer, and then you had the facade consultants all working together. And it was figuring out how you have these giant curved pieces of glass in Connecticut, which gets winter. And so there was a lot of thermal modeling. There was how do we, what are the right coatings? What is so in terms of like maximal system sophistication, I think there's that. And then the final project is this like gorgeous, minimalistic kind of, it's like if you think of like Hobbit-esque Shire scenery with like this super elegant glass strip. So that's probably one of the nicest ones that I've worked on that I like. Yeah.
From a sustainability standpoint, what's the R value? How's our
Yeah,
our
wow.
envelope
That's a we're wading into like hot topics here. So there's the R value is almost exclusively going to be a function of, there's some coatings and things like that you can put on glass for UV transmission and low E transmission. So there's coatings, and then there's the big sort of efficiency is going to be your IGUs. So there's double glazed IGU, and then there's triple. There's a whole debate about the two, double to triple glazing.
Sounds better. No one's nothing about that.
But then like you have to look at the life cycle and so I think when you're looking at glass and facades in general, ETFE, but glass specifically, you really have to look at a whole life cycle cost analysis because glass is very energy intensive. It to date is not really recyclable. Because you've got this inner layer and all this kind of stuff. So you have to be like ruthlessly honest to say like, how can we come up with something that's maximally energy efficient, But every time we add like a UV coating or a low E coating or things like that, you're adding more high energy, high intensity things. And also, you have to look at this as a system. So per square foot, the glass takes up a whole bunch of area. But in terms of my thermal breaks and all this kind of stuff, it's going to often be at these connections. And so the detailing there is oftentimes, again, devil's in the details kind of thing. So the detailing there is where you're going to have a lot of your thermal transmissivity and things like that. So we have to detail out those. And if you want to play around with something, there's a great software out there. It's Therm, and it's free because it was developed in conjunction with tax dollars. And so I think if you Google like Therm 3D or something like that, it does a really nice job of modeling some of these for our values and all that kind of stuff.
Well, I have a last question I want to ask you that's not related to these at all. With both being a practicing engineer and a professor, which is probably fairly rare to have both and to see that, what do you wish all young engineers knew?
I'm trying to think how to articulate this as succinctly as possible. The purpose of engineering is insight. It's not numbers. And so one of the best ways to get that insight is to get out on the construction site as much as possible. So it's kind of the crib. I think it was Hardy Cross, right? It's like your analysis is essential, but otherwise unimportant. And so you need to go see how stuff actually gets built. You need to learn how to draw construction documents. There's a whole side of how things actually get built, and the art and the dark arts, right? Of like that. Yeah. There's a lot of like every schlub in the world who's an engineer should be able to design a beam. Mm-hmm. The purpose of engineering is not the numbers, it's the insight. So engineering analysis is insight, not numbers. I would say that's the key thing I wish all students would take.
I like that a lot.
I like that, yeah. If you could tell me that 20 years ago, that would be ideal.
Well, Joshua, thank you so much for being on the podcast again. We really enjoyed actually sitting down in person with you this time and chatting. So thank you so much.
Yeah, it was great. Thanks for having me.